Okay, so here's a nice summary of lesson 1.1, evaluating limits. So the first thing we have to know is we have to talk about the difference between the existence and the non-existence of a limit. So in order for a limit to exist, it has to approach the same value from the left as it does from the right. Now there are some cases where limits don't exist, and you'd want to make yourself really aware of three specific ones. Any type of one-sided limit discrepancies, where the limit is not the same from the left as it is from the right, oscillating behavior, and then unbounded behavior. And then finally, as we go into some examples of how to evaluate a limit, we want to make sure we understand what to do. So we'd like to at least try to directly substitute the value in first. If we get some type of indeterminate form, then we'll try some other things. Maybe we'll factor, we'll rationalize, we'll simplify a complex fraction. Every once in a while, we'll have to use some trig identities. So let's take a look at some specific examples. So this one's just asking us to evaluate the limit as x approaches -2 of this quotient. I can tell you now, if we do plug in -2, we will get 0 over 0. So direct substitution would give us that. So instead what we're going to do is we're going to try and use factoring. So what I'll do here is I'll factor the top. Now the limit as x approaches -2, and this will become 3x minus 1 and x plus 2. And what you'll notice here is conveniently, the factors x plus 2 cancel out. And now I'd like to evaluate what's left. So the limit as x approaches -2 of 3x minus 1, go ahead and plug a -2 in there, and we get -7. Let's take a look at another example. Now this one involves rationalizing. So when we see that radical, it's something we have to be aware of. Again, by direct substitution, we're going to get 0 over 0. So in this case, what we're going to try and do here is we're going to try and rationalize, which means we'll multiply the top and the bottom by the conjugate of what we see here. So here we go. Now just as a piece of advice here, what I think you want to try and do is not actually multiply these out. I think you want to keep them just as a product. But the top you would, because what will happen nicely here is when we multiply these first two terms, radical goes away. So now we're looking at the limit as x approaches 3 of x plus 1, and then inside here and outside here, things will cancel. We'll just have -4. Like I said, let's keep the bottom factored. I'm not going to go ahead and distribute anything through. And then when we clean up a little bit, the top will become x minus 3. So again, very convenient, just like our factoring problem. And that will allow us to recognize the ability to cancel. So these go. Remember, up here would still be a 1. And so to finish up, the limit as x approaches 3 of 1 over the square root of x plus 1 plus 2. And when we plug in now directly, 3 plus 1 is 4. 1 over 2 plus 2 gives us 1/4. So let's look at another example. What do we do with a piecewise function? Well, like we said before, functions don't have limits where they don't approach the same value from the left as they do from the right. So in this case, we'd have to look at x approaching 2 from the left and x approaching 2 from the right. So the limit as x approaches 2 from the left of 6x squared, plug a 2 in there, would be 24. The limit as x approaches 2 from the right would, well, there's nowhere to place a 2. So what we'd have to do here is you'd have to say, plug a 2 in for x, but there is no x. So this is serving as one big constant right now. So all we do is we say, well, this must equal 4a minus 7. So it says find the value of a. Well, in order for this limit to exist, these two things would have to be equal. So what we'll do is we'll set them equal to each other. 4a minus 7 equals 24. So when we solve that, a would have to equal 31 over 4. And you can even plug this back in to go check to make sure you get the same thing. And when you plug 31 over 4 back in here, you actually do get 24. So it makes a little bit of sense there. Okay, so finally, Let's take a look at one involving trig. So again, on the surface, if we were to directly substitute, we put pi over 4 in here. Well, tangent of pi over 4 is 1. So 1 minus 1 is 0. And then sine and cosine both have the same value at pi over 4. So that's going to be 0 over 0 again. So in this case, what we'd like to do is maybe think about using identities. And here, we notice that we have 1 minus sine over cosine. And what I could do here is I could actually work with that top a little bit. I can maybe make a least common denominator and see what that gets me. So when I do that, I get cosine of x minus sine of x all over cosine of x. Now, all in one breath here, what I'm going to do is I'm going to keep in mind that all that's over 1. So I'm going to go ahead and flip that now. And what's good about this is some things are going to cancel. Now, what I have to understand, though, is when these things cancel, they're not exactly alike, right? They're differences. So they are off by a factor of -1. So here's my final problem. The limit as x approaches pi over 4 of -1 over cosine of x. And so now I can attempt to plug in pi over 4. When I do that, I get -1 over radical 2 over 2. And so I want to flip this up, clean it up a little bit. -2 over radical 2, rationalize, and we just get negative radical 2. So I hope this video has been helpful. If you need further practice, I would just suggest going into your book, taking a look at some of the homework, or obviously stopping in for some extra help.